So, just a quick recap. Looking at 3D density fields that vary through space, we're going to be looking at using Perlin noise. And basically what this does is gives us a density value that varies through space. They've got some links on explanation of those noise functions if you're curious about that. And for right now, we're just going to consider those as something that gives a value for any point in space. So in the ray marching program, we're going to be integrating along the ray. We start as fully transparent and then loop through a number of steps. I'm going to see that the t value, that's the parameter that lets us see how far we are along the ray. We say that that's the step size, that many steps out into the world, I guess, from your minimum t value. That's where you started marching through the volume. So you get your sample point by adding the that ray direction times t to the ray origin. So then we get a sample of the density, and we can get the attenuation at this step by taking the exponential of the negative density times sigma t times the step size, and then multiply the transmission value times this this attenuation factor. And so they've got a picture of what this looks like intuitively. This is at those points, we're doing the same calculations as what we saw last time, except now density is an extra factor in this function, so that scales the contribution at each step. And so you can kind of see where that starts to add some more non-uniform features to the volume, and you can see how that adds something of a more natural look to it. So this is a rather simple change. So instead of just being a constant density, we're going to go ahead and use that noise field instead. When the density field, we sample the density field as we march along the ray, and use that noise function. Okay, so for each sample along the ray, evaluate the function, the sample as the function input parameter, and use the result as a value for the density at the point. And figure 3 shows it applied to the sphere. Be sure you understand what's going on here. We plotted the noise function over some distance and the transmission value over the same distance using that same noise function for the density. That result is shown in the image below. We've also plotted how Beer-Lambert law would look if that had a constant density versus a space-varying density. As you can see, the green curve, constant density, is perfectly smooth, where the red curve is not. Okay. So if you just have a homogeneous volume, it's going to be a constant attenuation, where with a heterogeneous media, it's going to be, you're going to have, it's going to be greater and smaller density variation. So you're going to have less attenuation on, I guess, depending on the expected value of the noise field, but it generally will attenuate slower here, is what they're showing, I guess. So they're just sampling through, just showing kind of what that looks like. So there's a problem. The code works to compute the volume transmission value, but the code has been using to calculate the in-scattering contribution will not, as so you've got to add the variable density to the shadow ray, basically the light. To going to the light. Otherwise, you're treating it as if for that first bounce, you're treating it as if it's just uniform, and so that the lighting won't necessarily be correct, I guess. So that's the incoming the LI term. So you need to explain what changes we need to make, and then get it to work with the heterogeneous media. So looking at figure 4, we can get a sense of what the problem is. For homogeneous volume, all we had to do was get that distance to the boundary in the direction of the light. Then apply Beer's law using that distance and the volume extinction coefficient to find out how much light we are left. So sigma t was a constant in that case. So now adding the density to that, we've got a scale factor there that now indicates how dense the space is as we go through. The problem with heterogeneous volumes is that this is no longer valid since density value. So rather than this being a constant, it's now going to be a sample of our density function. We're not solving the same problem as we did in chapter 2 with the forward ray marching. The reason we used ray marching so far was to estimate the in-scattering term along the camera ray. The ray marching technique will be useful again here to estimate the in-scattering term, as well as to estimate the camera and light rays transmission as they travel through the heterogeneous participating media. Not the same problem because this is just in terms of distance. We actually have to be looking at something similar to what we're doing for the primary array, where we're taking those steps with the varying density sample along the path there. Need to break the ray into a series of segments and estimate the transmission, same as what we do for the regular ray march, the initial ray march. Multiply the total transmission value there by the sample transmission as we move along the ray. So we look at, this would be kind of an inner loop here to go towards the light, basically. And they're saying, okay, yeah, if you're going DL distance, then you take some number of steps, then you know you're going to take a step of that size. And then you can also use that again when you're doing the Beer's law stuff, because that distance still has still affects the equations in the same way. But one of the big things there is that, well, maybe a little out of scope, but the idea there is if you've ever looked at like Riemann sums for integration, that's basically like the trapezoid rule, or not. No, it's like the rectangles where you sum up the area under the curve via the rectangles. When you just multiply by the step size there. That's kind of the width of the triangle, or not, width of the rectangle, rather. So if we compare this code to the code we used in the previous chapters, we can calculate the rate transmission value as we go from T0 to T1. Okay, and so okay, so this is the old code with the constant density value. So they're looking at doing the same thing, just a math trick that we haven't spoken about. The transmission value is essentially a series of exponentials multiplied by one another. If you unfold the ray marching loop, you get something like this. And if we were to rewrite this code using mathematical property of exponentials, we get some sum of noise values, and we can get that value tau, and that gives us, we're back to that same exponential from before. We can use in place. Well, Yeah, tau is the sum of noise values, so we can use that to just use that to calculate the transmission once we have once we decide to stop, I guess. So all we needed to do to accumulate the density values at each sample is then use the sum to calculate the light ray attenuation and transmission value in a single call to the exponential function at the end. So yeah, using the sum of the noise reads. You could technically do the same for the camera ray transmission value, but note in the code provided below, we use the transmission value as an early out. Or no, rather, to attenuate the Li term. So it's also useful as an early out if that goes below some threshold. We need an intermediate value of the ray transmission as we progress through the volume, which is the reason why we don't just sum up the densities into a variable and calculate the final ray transmission at the very end, as we do to calculate the transmission of the light rays. So I guess this is a simplification that we can use for the attenuation on the way to the light source, but less useful for the main ray march loop. So if we look at the code here, we've got transmission value needs to be multiplied by the exponential at each step. And then we could do the yeah, because it needs the transmission at the end when we're adding to this result value here. Right. So as we take those steps towards the light source, we're sampling through the same noise field, and they also have a constraint of a sphere. So that's just kind of showing what the situation is there. So homogeneous, we're just looking at that constant attenuation based on the distance. Whereas in a heterogeneous medium, we got to take those steps and effectively just integrate that. It's just a little bit more complex because it's not a constant density there. But again, that simplification makes it so you only have to do that one time. Tau is not chosen by mistake. You find it being used in literature to denote a quantity called the optical depth. That's how much stuff is there. So Greek letters are often used for this quantity, either tau or rho. Rho is density a lot of the times. So we won't give a formal definition for what optical depth is, but they have another chapter, which is maybe later. I'm not sure. So okay, that's it. Now you have everything you need to render an accurate image of heterogeneous volume objects. This last figure shows the transmission curve, what it looks like for a given noise profile. And so here's that. What I was talking about, you're effectively integrating with, the step size sets dx basically, and your how good a result you get depends. You have to pick that step size well in order to get a good result out of it. Okay, so, and we're looking at the attenuation in the same way. So practical implementation, let's look at the necessary adjustments to our program to demonstrate how this would work in practice. Remember that the algorithm works as follows. First, we're ray marching along the camera ray. At each sample along the camera ray, we estimate the density at the sample location to calculate the sample transmission and estimate the in-scattering contribution. So we ray march along the light rays second. Before we only marched along camera rays, we now need to ray march along the light ray as well For homogeneous volume objects, we only need to march along the camera ray, but heterogeneous, we do need to consider this second ray, steps along the second ray, because it's not uniform. Yeah, so in other words, we need to ray march along both the camera and light rays now and evaluate at each sample along these rays a density function. So that's currently a Perlin noise function. It's a lot of operations. So you can tell that it would be a significantly larger amount of work than the homogeneous medium. One of the big things there is, well, depending on your situation, you may or may not do better to cache that to a tiling 3D texture or something. Depending on what noise function you're actually using. It could be cheaper to do that or not do that. It just kind of depends. So function is now called by the integrate function. Evaluate the density. Okay, good. Density of the heterogeneous volume sphere at sample position P. Returns the value of the Perlin noise function remapped to 0 to 1. Okay, so then they've got some scale factor frequency here. And that's just effectively just, yeah, it's scaling the point. So that's your sample location. You're going to change the size of the features in the noise field. So when you're integrating along that from ray origin and ray direction, you can take, yeah, so we're establishing that we're taking some constant step size. We've got these coefficients established. Okay, and then they have a couple of other things that they haven't explained yet. The phase, well, I guess we did touch on that phase function, and then I don't think they've talked about the Russian roulette yet. That's basically just a way to do early out as well. So NS is going to be number of steps, and take, yeah, that distance between the 2 points divided by the number of steps to get our step size. Some constants for light direction and light color. Transmission initialized there, and then we're ray marching. Okay, so for number of steps, we're going to jitter the sample position. I think we talked about that briefly anyway. That's basically just offsetting, so you're not taking these constant size steps in the volume, because that can create aliasing issues. Dried light is going to be and depending on your situation, you might just take a constant number of steps on the shadow ray, or you may want to try and like look at your bounding volume distance to the end of it from the inside, and then pick your number of steps based on that. It just kind of depends what looks the way you want it to. So again, we're just ray marching along the light ray. And then they're functioning. They're also applying this phase function here to basically scale the contribution to the output by the direction. So it's negative ray origin. I think that should be ray direction. But the idea is that, yeah, you've got the light direction, you've got a ray direction for the camera, and by looking at those two vectors, you can evaluate the phase function, and that's going to scale whether you're getting more backscattering or forward scattering. So what they're doing with the Russian roulette, I guess they're just generating a random number, and if it's greater than 1 over d, which is your probability value, then you break out of the loop. It's the main Raymarsh loop. Okay, so yeah, you got some probability to break out of that loop, and if you don't, then you multiply the transparency by this factor. So that's just a way to do early out. And so we get the background color, again, times the transparency plus the result. So that's the in-scattered light is informing what the result is. The background color is allowed through at a certain amount that's informed by the transparency that we got. That's the attenuation through the volume. So that's our camera ray went through this much stuff. So in this implementation, step size used for the camera and light rays is the same. This doesn't necessarily need to be. Speed things up, you can use a bigger step size to estimate the transmission values, or yeah, however you want to do it. There's a lot of different ways. Now that you use a procedural texture, you may encounter some filtering issues. The frequency at which you sample the noise function is too low. You may miss some of the fine details from the texture, and you will get aliasing issues. So again, filtering issue we won't be digging into right now, but be aware that step size, noise frequency, and your resolution are all kind of connected there. They're all going to have an effect on how this turns out. Might be surprised that the program output on the right doesn't look more like a cloud already. But as you can see with an image of the noise pattern, the lumps making up the noise are rather smooth by default, which is why the volume has a smooth appearance as well. The art of making cloud-looking procedural noise involves tweaking the noise function. There are book chapters on this. There are papers on this. There's a lot of information out there about that. A lot of times, what they do for these is they use a combination of Perlin noise and Worley noise, which basically, yeah, there are ways to combine different types of noise to create something that's more like the features you see in a cloud, or you can tune that for whatever type of medium you want to try and model. So removing negative values from the noise function, or taking the absolute value of the noise function, two different ways that you could shape that into a noise field that you like. Fall off parameter explained further down is, yeah, it looks like basically what they're doing is yeah, it's a scale factor. However unspectacular, this is the exact technique that was used to create the effects in Contact, the opening sequence. It's created using Pixar's renderer and created by Sony Picture Imageworks. Sequence is a huge technical undertaking at the time, especially 1997. That's like supercomputer territory. As mentioned before, they use some of the same techniques as the one provided in this lesson. This difference is they use some geometry, not basic spheres, to define the shape of the volumetric objects, and some fractal patterns to help give a cloud-like texture. So that's the finer variation is going to be coming from like a noise something or other. And then the larger features are going to be bounding volumes, like what they were doing with the sphere. As for a cloud-like texture, let's see what we can do. Play with the density function to create more interesting looks and animations. So creating cloud-like procedural textures is different than just using some off-the-shelf noise function. It's more of an art type consideration. You've got a series of mathematical tools to help shape the procedural texture and spend a lot of time tweaking the parameters until you get something you like. Your goal here is not to create convincing and wow images, but to give you the tools that help you understand how things work and that you can eventually recombine into more complex systems. A few tricks you can use to create more interesting cloud-like spheres. It's just a short selection of some of these tools. And so the smooth step function is a type of remapping function where you can it's a smooth version of the step function. Step function is 0 for any negative values, it becomes 1 for 0 or any positive values. Smooth step is it's essentially that, but it has a bit of a transition time, so it's smooth. It's not just that sharp change at 0. And you can look up kind of what different usages are of that. There are some good videos that are just focused on smooth step. We can use this function to create fall off near the sphere boundary. To do so, we create some changes to the eval density function and pass that as parameters to the function. So that's the sphere center and the radius, or whatever you want to use to parameterize your sphere. So here, what they're doing is they're saying the smooth step starts at 0.8 distance and then ends at 1. So we, or maybe the other way around. In any event, the idea is that you have a fall off from this distance to this distance. And that's one way that you can kind of tune those. That just from the uniform volume, you can change that to something that's got slightly more features to it. Useful for fading out the volume before it reaches the boundary of the sphere, rather than having a sharp transition there. We use the smooth step function to control how far from the edge the fall off begins. FBM, known as plasma or chaos texture, in the good old times as fractal Brownian motion. That's usually multiple octaves of noise combined, either scaled or rotated or etc. In between, in order to add more features of different frequency and kind of break up the periodic nature of things like Perlin noise. So it's a fractal pattern made out of sum of procedural noise layers for frequency and amplitude. So amplitude here is just scale factor on those things from layer to layer. You can find some more information on that in the procedural generation section. So typical structure there is going to be like this. We establish some frequency. And this lacunarity, I'm not sure how you pronounce it, but this is kind of essentially it's how much the frequency changes at each step. Or no, at each iteration of each octave of the noise that's being applied. And then they're clamping to a minimum value. Right. So you can very quickly start to look at something that's got a lot more interesting features. And that's because you go from something that has only this very low frequency component. You see that the kind of lobes are very large because they're happening very slowly in terms of space. This is spatial frequency. Here we've got a lot more high frequency involvement and starting to look a little bit more maybe like the cloud. Biasing the the noise function value shifts where the center, that's kind of the expected value. We're shifting that to some offset amount. This is one way you can do that. That could even be as simple as just adding and then clipping again, but here they're doing it with the power. Rotate the noise pattern using the primitive local frame. Animate the noise pattern within the volume. Okay, so I guess maybe it's something that's specific to each sphere if you have multiple spheres. Sample position we pass to the density function is defined in world space. We can define this in kind of sphere space, object space. Define this sample point within the sphere reference system. All we need to do is, figure out where it is relative to the center of the sphere. More generic solution would consist of transforming the sphere using matrices. It's transforms. However, we're not using matrices here, but you can do this easily with the information on the other Scratch Pixel tutorials that deal with more raster stuff. You'll be seeing a lot of that if you go through those. So you look at like rotating in between different for different primitives or these bounding volumes. You could look at rotating it. You could look at scaling it independently. But here, for just one in particular, you could look at a situation where you keep the same volume elements inside of the sphere because it's you're sampling relative to the center rather than in world space. Similar to veins of a glass marble, the pattern sticks with the sphere regardless of the transform. In the example we chose to illustrate the idea, we'll be rotating the point in object space around the primitive sphere y-axis. Better solution would be to rotate the sphere using a object world matrix and then transform the sample point from world space to object space using the world to object matrix. But we were too lazy to do it here, so we decided to rotate in object space instead. Just about the center is pretty easy. So as a result, we can see the fractal pattern rotating as well, a bit like if you were looking into a marble. More sophisticated deformations can be applied. You can look at, nonlinear transforms. You could shear it. You could do any number of things. So they're looking at basically extending what they were doing before with the FBM, but now we have a stage where we're getting this new sample point from some transforms here. And okay, so then we can kind of see what that looks like when it rotates. So that's pretty cool. There's a lot of other tricks you can go on and on with displacements. That's if you want to displace the edges of the volume using a noise function, different types of noise. All types of noise you could use for this. So going over what we've learned so far, what you can do now is use raise marching to render a single scattering heterogeneous volumetric object. This is already a pretty big accomplishment. Another thing that should be clear by now is that with ray marching, we break the volume object down into smaller volume elements defined by the step size. This technique works because we assume that these tiny volume elements or samples are small enough to be homogeneous themselves. And that's one of the big simplifications we make when we're integrating like this. In short, though the bricks themselves can be different from one another, it's a bit like when you build an object out of Lego bricks. And if you take this to different contexts, you could use a 3D texture there as well. And then those bricks are the texels in the texture. And so they've got source code, and that is the end of the chapter. Do we want to look at the next one, or what do we think?
I think we can stop here.
Cool.
Thanks for reading all that.